Hi, everybody. Thanks for joining us today. This is Nathan Nichols, Marketing Manager for Metascale. I have Amit Seed, Senior Development Manager. He leads curriculum development for training and use of big data technologies with Metascale, as well as Alex Razin, who's a professor in mining big data with a background in relational databases and database processing for analytics. Today we'll be talking about driving business analytics with data mining and machine learning. For just a quick background on Metascale, we are a wholly owned subsidiary of Sears Holdings Corporation. About 4 years ago, Sears started its big data journey, implementing Hadoop into its traditional relational database warehouse. And based on that learnings, we developed Metascale to share information on, how do you implement Hadoop into the existing environment? How do you use big data technologies to gain value from all of your data? And part of that process, we developed data analytics. And today we're going to go into a little more about data mining as well as machine learning with Mahout. And with that, I'm going to pass it over to Amit to go a little more in detail. And before I do that, just a little note. As we go along, feel free to send any questions you may have via the chat function to me. And we will have a Q&A session at the end. So raise any questions you have as we go along, and then we'll address those at the end. All right, Amit.
Hey, Nathan. Thanks a lot for that introduction. So today, we're going to cover a couple things. One is, what is big data? There's a lot of different terms out there, a lot of different concepts that are associated with big data. So we want to give you a good idea of what that is. Using Hadoop for big data analytics, the evolution of analytics, and techniques used for analyzing your data. So what is big data? Big data can no longer be defined by the amount of data, but by the type, speed, and storage capacity needed to compute and analyze data. Typically, when you hear that term, big data, again, when you hear that word big, normally most people immediately assume that we are referring to size. When size is one element of data, but it's not the only element and not the only component that goes into what is actually defined as big data. So as you can see, data, and more data. Within the last 2 years, the world has created more than 90% of the total data that is available. The data that is out there is coming in a wide variety. Some of that data is structured, regular standard numbers, that you're getting and that you're able to actually crunch and process. But then there's also a wide variety of types of data. You think about YouTube videos, you think about blogs, emails, text. The data is that is out there is ever changing. And really, with that being said, that data typically, when we look at types of data, we look at kind of 3 V's, and the V's have actually kind of changed. Some people say there's 5, some people say that there's 6, but the 3 V's that we really look at are, volume, so the amount of data you have, or the scale of that data, velocity being the speed at which you're receiving the data, so whether that's batch, whether that's periodic, near real-time, or real-time, and also variety. Again, this illustration here really shows you the variety there. So the type of data you're processing, whether it's structured, unstructured, photos, videos, etc.
So I just wanted to add a couple of things from more of the academic perspective, I suppose. One other fascinating thing about big data is that if you look at, there's this nice slide that lists all of the types of the data that are being created every minute. On top of this, however, the biggest part of the data is not necessarily the content itself, but rather the metadata that exists on top of the things that are being generated. So one example, Twitter, no matter how many tweets are being sent over the wire, every tweet is famously no more than 140 characters. However, if you look at the entire contents of the data, which includes the followers, the likes, the user profile, the time it was sent, where it was sent from, that goes to well over 2,000 bytes on average. So for every byte of data, there's probably 5 or 10 bytes of metadata that are being generated. And for all of the internet usage, there is the log of access, and there is the information of who and when and how it was done and so on. So there is even more than you would think.
Oh, yeah, definitely underlying. So how big is big data? So if we think about, data as being a grain of rice, that would be your standard just byte of data. As we move up, a kilobyte would be roughly a cup of rice. When you think about a megabyte, you're talking about 8 bags of rice. We think about a gigabyte, we're looking at 3 semi-trucks full of rice. When we look at it terabytes, we're looking at 2 container ships full of rice. When we're thinking about a petabyte, that's enough rice to blanket the city of Manhattan. When you think about an exabyte, that's enough rice to blanket the entire West Coast. When you think about a zettabyte, that would be the amount of rice that would fill the Pacific Ocean. And then when you think about a yettabyte, it would be an Earth-sized rice ball. So, with that being said, the NSA, so the National Security Administration, is actually going to be building a new data center outside of Salt Lake City. That data center, to start off, will be housing roughly anywhere from about 3 to 12 exabytes of data. But what they're looking at is actually getting a storage capacity that hopefully by around 2015 should reach close to a yettabyte of data. So when you think about the amount of data that someone like the NSA is probably looking at, it really goes to show you the the volume and again the type that we keep reiterating of data that is out there.
Yeah, and one more thing to add on the same discussion. On top of the fact how important visualization is, it's also the case that big data means different things to different people in an organization. Arguably, it's not that 1 yottabyte or 100 zettabytes is big data. More than that is big data, less than that is not big data. But rather, it's whenever you start to exceed your capacity, and that also has to do with the kind of data you're dealing with, how structured it is, and what kind of existing infrastructure you have in place. So as soon as your infrastructure no longer keeps up, this is where you hit the big data threshold.
And to that point, Alex, yeah, definitely regardless of your, if it's a gigabyte or a yettabyte of data that you're processing, you always want that data to be processed quickly and efficiently. And, one of the problems that a lot of organizations have run into is, they see the data that they're getting. They know that, hey, there's a lot of stuff that we can, do with this. There's a lot of ways that we can make, our business better, make our processes better. But, oftentimes there are, challenges that go into, processing, large amounts of data. And, with traditional computer processing, it can be difficult to compute everything, due to storage space, processing time, cost. I mean, it can just be a challenge for typical machines. Normally processing units are not, built to handle, the volume, size and, speed of the data that's coming in today. And, if you are looking to actually process that data, quickly and effectively and also be able to store that data, it can get quickly not cost effective. The amount of money that you'll be spending to actually be able to process that data effectively goes up pretty quickly. And, this typically, when you're talking about processing large amounts of data as well, it typically can lead to, incomplete computations, data latency, and, an overall lack of quality analysis on that data. So with that being said, big data technology that is in place is, Hadoop. It brings, infinite scalability. It processes large amounts of data extremely quick, has a pretty much infinite storage capacity as well. So as I mentioned, Hadoop. So Hadoop runs on large clusters built on commodity hardware. It provides reliability and data motions to application, implements a computing paradigm named MapReduce, applications divided into small frameworks of work for execution and re-execution, on any node of that cluster. Also the second portion of, Hadoop is the HDFS file system that stores the data and computes the data on the nodes, results in high aggregate bandwidth across the cluster. Both MapReduce and HDFS, automatically handle node failure. With that being said, Hadoop has, really because of the cost of hardware going down, when you think about initially when computers first came out, they were well over $2,000. But now it's very simple for you to go out and buy extremely high quality and powerful laptop for less than $300 to $500. So with that being said, a process like Hadoop that really is built on commodity-based hardware allows you to quickly add speed and storage space in an area that typically a while ago would not have been processed just due to the the extended amount of hardware costs.
And in general, so the big selling point of MapReduce and therefore Hadoop. So the big selling point of Hadoop would be the fact that it's open source and freely available. But the big reason why MapReduce has gained so much popularity is this idea that Omid mentioned, that you can split up your computation into many participating computers without having to do a lot of coordination. The big issue with distributed databases in general is that there comes a point where once you have dozens or hundreds of machines, the amount of communication required to keep everyone in check and to be working towards the same result is becoming prohibitively expensive. So the MapReduce paradigm is this idea that you could break up your computation into nearly independent pieces, that everyone can do their work with very little communication with the coordinator. And that's what lets you scale. The word infinitely is a little overused, but the current clusters do scale to thousands of machines. I think at about 5,000 to 10,000, the current implementation of Hadoop is starting to have problems. They are working on the Hadoop 2.0, which is supposed to go higher and be a little more scale even further.
So some of the advantages of using Hadoop, as again, outside I've kind of briefly touched on, are again the scalability. So easily adding commodity-based hardware to your system, and then being able to store and process petabytes of data. The great thing about Hadoop is with typical machines, if you are adding additional power capabilities, it typically is going to lead to downtime because that machine has to be turned off, additional machines have to be turned back on, data has to be transferred over, and it's can be a long and arduous journey. With Hadoop, it's pretty much as simple as you add that commodity-based hardware, so that server, and then you do some basic configurations, and then when your system recycles, it notices that server is available and begins pushing data towards it. So really no downtime for the user, when you are, adding additional, resources to your, to your current process. Economical, again, we've, touched on, the how hardware has really decreased in price, so it's easily to, easier to add that commodity-based hardware. It's very, very powerful and, has a great processing ability, which really goes to its efficiency and reliability. It replicates your data 3 different times in 3 different locations. It's really built as a fault-tolerant system. With any hardware or any, processing engine that you're using, systems are going to fail. It just happens. I mean, no computer system is perfect. But Hadoop, really, it takes that failure and it, kind of just goes with it and really has no, the system corrects itself. So to the user who's processing data, if you do it, say, for instance, have a node go down, you really aren't going to see much, difference in your processing just because, again, the jobs are spread across, multiple nodes, multiple servers. So it really allows the user to really not see any effect when systems do go down. And then also storage capacity. Again, it's a central repository, an enterprise data hub, as we often call it, where you can really keep everything forever.
Yeah, a couple more notes on some of those bullets, which I think are also interesting. So first of all, the scalability is also able to incorporate different kind of hardware. I think that's a very big selling point of Hadoop as well, where you can plug in a machine that isn't as powerful, either slower or faster than the rest of the machines on the network. And in the way the computational task is distributed, it just ends up doing the respective amount of work. So in your typical database, it's actually tricky to have fast and slow nodes working together. On the economical point, Hadoop isn't automatically a win. In fact, there is some sort of a trade-off point where, because the processing capacity is linear to the cost of the cluster, since you can just linearly scale it, there comes a point where Hadoop should be able to outperform a higher-end machine. That point doesn't happen at the 3-node cluster, but at 50 or 100, you outpace the high-end machine because the faster servers, like Teradata type hardware, is still pretty expensive. And one more point on reliability. So the ability to replicate the data serves as a way to recover from failures, because every block and essentially every file is stored in multiple instances. What I think is interesting is that the same capacity can be used to improve performance, because by having extra copies, which are spares for case of failure, you actually have your data in several places, which means potentially you can read it faster, or you can use the machine that's the closest or the least loaded, as there are multiple places to choose from.
Yeah, so as we're, looking in kind of the analytics portion of things, really that's where you're going to be combining, the power with Hadoop, and then allowing you to hopefully answer some of those questions that you want to answer. So really, this is where organizations begin to become, proactive rather than reactive. Understanding their business, and their customers. So, it's no longer a situation for most organizations out there where, you can just make assumptions about what's going to happen. Really, to be an effective organization, you need to understand the factors that have gone into your successes and also your failures. And then from there, analyzing that from an analytical perspective, so you're not just, more or less doing guesswork. You really kind of have almost facts behind why things are occurring. You can see trends, and, you can look forward, really, again, reiterating being proactive rather than reactive. So, again, when you're looking at, data analytics and some of the questions that, a lot of individuals are looking to answer, how can you better manage your inventory? So, again, you're not, wasting, valuable, retail space. How can you better understand, your customers' buying habits? I mean, regardless of the organization that you're in, you're going to want, again, those customers to buy more products, to be able to cross-sell to those customers. Also, again, understanding their buying habits. You also want to, for instance, for some organizations, detecting fraud. Understanding, what activities, are seen to be fraudulent, and how they're linked to other factors that go in there. Understanding how organizations can really improve decision making, and that goes back to point kind of reiterated earlier. Again, that proactivity rather than reactivity after the fact, and then how do you get customers to purchase more products?
And just one more point. So we just talked. Just a couple minutes ago, we talked about storing everything forever in the Hadoop cluster and then reprocessing and transforming it continuously. That fits in with this topic where you want to be able to answer a question, and one big step in actually doing data analytics is figuring out whether the data you have is sufficient to answer that question and whether you have enough. So the significant part of doing the data analytics and predictive analytics is in collecting the data you have, doing some cleaning, transformation, then probably going out and trying to scrounge up more data until you have enough to be able to answer those questions. Sometimes the general question of how can I get customers to purchase more products doesn't directly connect with some of your data, or requires all of it, or maybe some external additions.
Yeah, very true.
So just to give you a little bit of a hierarchy and to figure out where the predictive analytics and data mining tasks fit in, this is all under the edges of artificial intelligence, which has a lot of components, obviously. Within that, we have machine learning, and the next slide will talk more about this. But the thing, sort of the part of interest, is the ability to look at your data and essentially model its behavior. And in some cases, not only look for the correlation and connections within the data, but rather create a model that might tell you something about what to anticipate. Because, for example, if you're trying to answer the question of how can you get customers to buy more products, it's not just figuring out which things are affecting their decisions, but also trying to figure out which is most likely or will affect the decision to the greatest degree. And that's the predictive analytics part, all of which relies on significant statistics and math knowledge to make this work. So in general, as we mentioned, machine learning is the ability to process, extract, and learn from or derive correlations from data. Obviously, there are many applications. We'll mention some of the business ones. But in general, you take your data, you convert it into some sort of symbolic representation, and then you come up with a model that tells you something about the correlations and the connections that exist within the data. And data mining specifically looks for patterns, which sometimes is the correlation, like which things cause customers to buy products, or what causes the customer to leave, to terminate their service, or what causes new customers to become interested in the service. It may also, however, be the anti-patterns, and we'll talk about this in a second, but if you're looking for things like fraud detection, you're not really looking for a grand trend within all of your data, but rather you're looking who is the odd man out, which transactions don't look right, which transactions don't fit into the pattern. And that's also a pattern identification type, except that you're looking for something that's outside of the common pattern that you already have. So Mahout is one of the components within the great Hadoop ecosystem. We've already talked about Hadoop. Within Hadoop, so-called Hadoop ecosystem, there is maybe a dozen or 24 different components which all belong and somehow fit in to the general framework. Mahout is essentially a data mining library which has a number of standard data mining tasks pre-implemented in Java, and they're running on top of the Hadoop framework. So the tasks are already pre-implemented. If you can get your data into the right input, you can feed it to the algorithm and to the code, and that will deploy the data mining task on the Hadoop cluster and come back with the right answer. So some of the applications of the machine learning that you could use, obviously there are many more. Those are just some of the examples. So one example is spam detection, where you might be able to use a large body of emails which have to be classified initially. So you need to have a large body of emails, and you need to have them tagged by someone. So there has to be some sort of learning material from which the data mining algorithm can figure things out. So once you feed some number of thousands of different messages, and you specify which ones are spam and which ones aren't, then the data mining algorithm, machine learning algorithm, can figure out what are the categories, what are the properties that define the spam message based on a collection of existing data. And you can actually refine this model. As more creative spam is being sent, that can be added to the body of here are the spam messages, and the new properties can then be extracted. Sometimes you can even see, if you get a message marked as spam, you might be able to see a little bit of note that says, here's the spam score, and here are the properties that caused it to be marked as spam. So you could sometimes even figure out what are the variables that affect something looking like spam, especially if the message is legitimate. Another example, as I mentioned, trying to detect fraudulent activity. In this case, you're not so much looking for the normal patterns and correlations, but rather you're looking for anything that stands outside of the regular behavior. And I talked to some data analysts. One interesting thing is that sometimes your learning algorithm does so well that it doesn't account for some other external factors that aren't actually in your data set. Right? So if you have this collection of credit card transactions, you can figure out what things cause something to look fraudulent and what doesn't. And one example is that typically big-ticket items that happen at 3 a.m. or a large number of big-ticket purchases that happen in the middle of the night, that's almost immediately a sign of fraudulent activity, and most of the decision systems will figure it out. However, what happened recently is that the Black Friday starting date had been pushed up and up. While it used to be 8 a.m. or whenever it happened, they started moving it to 3, to 4, and sometimes even to midnight. And this is the point where you actually have to go in and adjust your model manually, because on any other night, a number of purchases of large TVs happening at 2 a.m. is a certain sign of fraudulent activity. But in this particular case, where the Black Friday is the reason that causes it in the first place. So some other examples are obviously facial recognition. Again, this is something you need to extract the properties that define the item. That's a general observation about the process of sort of data mining and machine learning. The algorithms don't look at the face as we do, as the composition of all of the pixels, but rather what you do is try to extract key points or representative points that will let you compare different faces. And the current strategy, I think the most prominent one, is to come up with a framework of representative points, I think 10, 20.
Yeah, like Facebook is one where you probably will see that when potentially, you're going in and tagging a picture, and sometimes it automatically recognizes a particular individual in there. That's, one area that you probably see some of the facial, recognition things, and, kind of moving, on to some of the other just basic examples. We have like the speech understanding, Surrey. So any of you, individuals with the iPhones out there, that is a machine learning algorithm right there. Understanding customer segmentation, if you're looking at, really going out there looking at doing like, direct marketing or targeted emails, that's really where you can, understand, particular customers, behavior by looking at either, their current actions or past actions of like individuals. So again, you can make some of your marketing efforts more targeted. And then product recommendations, anyone who's used an Amazon.com, or even if, you think about some of the like frequent rewards cards that you get at, some of your shopping facilities, those individuals, when you, end up getting the, coupons in the mail for, the items that you're like, hey, I always purchase these. So that, again, it allows them to, see what, what products are more actually related to you. And, the Amazon.com, they do a really good job of, in my opinion, of really, recommending products that really relate exactly to, typically what you're looking for.
And one common thing I would say for those last three categories is, in all of the cases, you need the learning data. You need to collect some amount of data that tells you how are you going to figure out next steps. So for the speech understanding, if you remember, if you've used any of the speech recognition software, the first thing you typically do is to train it for your particular accent, your particular pronunciation, because whatever model is developed there is probably built on a perfect non-accented certain voice person, and you need to adjust it. Same goes for customer segmentation and recommending of products. You need a history, you need a collection of data on which you can build, and we'll talk about some of the examples. So the big algorithms that are built into Mahout and sort of large and allowed to answer most of the questions we just discussed are clustering, recommender systems, and general predictive modeling decision tree structures. And we'll talk about each of them individually.
Yes.
So clustering is kind of an interesting application of data mining, where the goal is to come up with a way to group together, to bridge together items that appear to be similar. And the interesting thing about it is that you don't necessarily know what you're looking at. So the idea is someone gives you a bunch of data points, and you can think of it as customers. And you may know some of the information about it, not other pieces of information. And you can develop a similarity measure, a function that tells you those two customers look very similar, depending on what properties you have. So it could be age, it could be history of purchases, it could be gender, it could be address, and so you could just decide that your similarity is in part based on where they're physically located, customers. And once you do this, you could combine, there are several standard techniques, you can combine together similar looking items within your set. One intuitive example that I really like to use is, suppose you started out with a population of dogs, and you needed to figure out whether there are certain categories or certain breeds that exist within it. And so one possibility is you look at the size, so the height and weight of each of the dogs in your data set. And then once you group them in two-dimensional space, where one dimension is the height and another one is the weight, the items would tend to naturally cluster together. So dogs of the similar breed would be both similar height and similar weight. And so all of them would sort of come together. And if there are several distinct categories, even without knowing what they are a priori, you would be able to observe them within the data by simply running this algorithm. And so this is one of the applications. Obviously, there are many others. Essentially, the general ability to do clustering lets you segment or partition the data without knowing that the partition exists. Moreover, some of the algorithms allow you to find the number of similar groups without knowing how many groups there are. So suppose you had a collection of customers for marketing campaign or for lifestyle or risk management. You could run a clustering algorithm based on whatever properties you know, and you can define a distance function almost on any reasonable collection of properties, as long as you think they're sufficiently representative of what you're trying to capture. And then you could run the clustering and come up with the grouping, which would tell you those categories look to be similar, and then you could look at them and maybe decide who you got in this category, depending on the kind of partitioning you're applying. And the clustering algorithm would also give you some sense of how many different categories there might be in your set. So there may be 2 different significant categories, there may be 5, and that's another part of what the clustering can do for you.
Yeah, and when you're looking at a system like Hadoop too, it kind of goes into a situation where, being able to store that amount of, the amount of data that you can store with Hadoop does allow you a lot more flexibility with regards to the things that you can take into consideration. Oftentimes, as we kind of mentioned earlier with large-scale data processing, you can end up in a situation where you do have to omit certain things just because you don't have enough space. With that additional space that you do get, in a framework like Hadoop, it does allow you to take into, numerous additional factors that previously may have not been able to be available to you.
So the second category we're talking about is the recommender systems, which are things you encounter every day, most likely. So if you use Amazon, if you use Netflix, Pandora, or any of the similar, there is a bunch of radio streaming services. On top of Netflix, there's of course Amazon and Blockbuster. All of them are working to come up with a prediction based on what they know about you as the user. So that's what the recommender system is about, or at least one of the big applications. I look at a customer or at the user, and based on what I know about them, I can try and come up with what is it that they may like to consider or to buy. And there is a couple of different categories of recommender systems, and those significantly differ in what kind of information and what kind of they use and what kind of abilities they have. So one type is the collaborative filtering, and this one is interesting because you can come up with a model or a framework to tell you what you might like without understanding what is it that the person is actually buying. So the idea here is that you look at your users, you look at the kind of things, either the kind of things they bought or looked at or searched for or rated or put in their wish list. And then you look at your other users and you try to figure out who are the people similar to Mr. A, at least on this slide. And you do this by saying, all right, Mr. A had liked those 5 movies, and here is 100 other users in my systems that also like the same 5 movies. From that, I conclude that they have similar tastes. And once I know this, I can see all of those other people that like the same 5 movies. What else did they watch and what else did they like? And those are the things you recommend to Mr. A without necessarily stating it. But that's where the information comes from by saying that people who are like you like this. And that's exactly, by the way, what the Amazon site is referring to when it says people who bought this or people who looked at this also looked at. And the interesting thing about it, of course, is that you may not have any idea what are the items you're looking at. You're simply relying on other people's preference of the item as a black box.
Yeah, and to Alex's point too, when you're looking at, like for instance, like a Netflix, one challenge that you can sometimes run into with collaborative filtering is if it is something that is, a little bit more specialized. So when you think about maybe like, an independent film that maybe not a ton of users have either like reviewed or looked at, it may have, there may be challenges in being able to actually recommend that to another individual, just because there may not be enough, data points for you to actually be able to appropriately, relay that information.
And so the other category of recommender system or recommendation is the content-based recommendation, which relies more on what they know about the user and on user's history. So that, on the downside, that does require understanding a little bit about the item that you're looking at. So if you think about movies, then there's a bunch of properties that are reasonably well understood. There's actors, directors, length of a movie, type of a movie, year, language, and so on. And so what I could do is look at the users and see what is it that they watched. And it doesn't actually have to be things that they watched, if that's what you know. It could be absolutely anything, including what they searched for, including what they actually liked without watching, or what they bought. If this is Amazon, you might actually know what they purchased. If this is Netflix, you only know what they have viewed. And from that, you can try and derive a prediction or a list of properties that seem relevant, that seem interesting to the user. So if I look at your entire history of the movies, I could say, well, you obviously like those 2 directors, or you obviously are a big fan of French movies. And from there, you can go back to collection of your items, in this case movies, and try to come up what else looks like what you prefer. And it's important to know that, especially with the movies, it's kind of convenient that when you're buying something, it's a little harder to tell whether you like it or not. So the very common assumption if you purchase something that you liked it, or if you looked at the item, it's because you need it. It may be that you looked at the item to leave a bad review, but this one is hard to tell. Right? With the movies, that's why Netflix pushes for you to provide a rating. Same goes for Amazon. That on top of knowing which movies you watched, it's highly helpful to know which movies you liked and which movies you hated. So from that, you could also say, well, you watched all of those movies, but those are the ones you liked. So that's what you go by, and you try to exclude things that you watched and hated. And once you have this list of properties, you can come up with recommendation to say that this movie seems to have the actor you like and the director you like, so you may want to watch it. One last point, and the trick or the difficulty here is, of course, that you're trying to find the similarity between similar items. So if I have a history of your movie preferences and likes, I can come up with a model that will probably be reasonably good about predicting what you may like. But it's not particularly helpful in deciding what kind of toaster you would prefer to buy, because the properties are simply not the same. And so that's kind of the difficulty. Once you look at the details of the item, it only makes sense to apply this to another item of the same type. And of course, there are plenty of, at least research-wise, there is plenty of work in looking at hybrid systems that try to combine all of the above, that look at the properties of the items, and they look at the similar users that exist within the system, and they might even look at the outside factors. So one example is you can do a survey based on demographic or some other information, and if you happen to know the age and other information about your users, you can factor that in, something about which kind of demographics or ages prefer certain types of movies, and you could put it all together into some sort of approximate recommendation. Okay, and the last category of data mining or predictive modeling is decision trees. I'll just say a few words about it. We can be pretty quick. Essentially, decision trees are this kind of model that, based on a number of properties, can tell you, can give you a predicted answer. The reason why decision trees are really liked is because they're very easy to understand, very easy to modify, and sort of work through. So to make this clear, we'll just work for a very quick example to show you how the decision tree is built. So here is your example data set where you're trying to predict whether you are or not expecting a big tip. And here is a list of properties. Obviously, in practice, they can be numeric, but there are ways to handle that. So here's a list of properties about the restaurant, and we're trying to predict whether or not we can expect to get a big tip, to give a big tip. And so the way it works, you figure out which of the properties seems to be the most correlated and the most predictive of the answer. And suppose in this case it's going to be the food. If that's the case, then we split our data on the food rating, so that listing 1, 2, 3 goes to the left where the food is great, and listing 3 goes to the right. Obviously, you start with the most predictive feature, and then you continue this process to split data further and further. So then we can split on whether the service is speedy or not, and then we can split the data on whether the price is high or adequate. Once you have all of the above, this is the decision tree. So it tells you which are the most important features in predicting the tip, and it tells you the rules about how can you model or predict what happens with the new data entry. So to give a couple of examples, here is a few more rows. So we use the first 4 rows to train our model, and then we can use the next 4 rows to make the prediction. And in this case, if the food is mediocre, then a well-understood rule answer says that the big tip is not expected. And we can run for all of those. So in this particular case, our model gives us the answers of no, 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 and yes, which, because 3 of them match and 1 doesn't, gives you a 75% accuracy. Obviously, the higher accuracy, the better the model, and you can train and revise your model as you get more data.
Yeah, decision trees are also used oftentimes as well for organizational decision making. It's a really effective tool to really kind of develop a pattern or a process on why certain things are happening, and then how to be able to actually react to those things based on the information that you have. And that actually concludes our webinar for today. Hopefully you guys found the information to be insightful. And at this point in time, we will take any questions that we've had come in through the chat.
Great job, guys. Really good overview of data mining and machine learning with Hadoop. We do have a handful of questions here, and everybody can feel free to keep adding. We are coming up on time, but we'll get through as many as we can. The first question is a pretty basic one. How does data processing work in Hadoop?
Well, that's a pretty loaded question. So at the very high level, what happens is you load your data into the storage layer, and you have the collection of files. And then each file is broken up into individual pieces or individual blocks, where each block is of the same size. And once you start your Hadoop, or the paradigm is called MapReduce task, all of the entire file has to be processed through the mapper and the reducer component of your system. And the nice decentralized part about this is that if I have a file that consists of 1,000 blocks, then I need to run 1,000 mappers on each individual block. But it doesn't matter where I do it, or in what order I do it, or if something fails, I can redo the processing. That's the basic idea. If we had more time, I could go into more details.
Sure. It's a nice brief answer, I guess, for a big question.
Yeah, it can be a few-hour introduction or a few-day course. It depends on how much you want to know.
Sure. And another question, kind of moving into the whole concept of big data, how much data is needed to perform an accurate analysis?
That's an interesting point. So as we've talked about some of the data mining applications, it really has to do with, first of all, what kind of question are you trying to answer? So if you're trying to look for a pattern, say, for the customer retention or restaurant quality, then you might not need a lot because the trends are right there and they're easily visible. If you're looking for things like fraudulent credit card detection, you might need a lot more data because you're actually looking for an outlier. So if you don't find a very clear trend, you can't be sure whether something is unusual or not. In general, the more data you have, the merrier. And it's also the case that the amount of data determines the accuracy. So in the previous example, we had a decision tree built on 4 different rows, and we've come up with accuracy of 75%. If I had 10,000 rows, the accuracy would probably be 95%. And on it goes. The more training data you have, the more informative you can be.
Yeah, if you think about, like, for instance, if you're doing, like, transactions, something that is very critical to your business or dealing specifically with, monetary amounts, you're going to want your models to be, as accurate as possible. So your threshold for, the data points that you need, will probably be significantly greater than, for instance, if you're just doing, some basic, demographic assessment, or something of that nature where it's not as, critical for the accuracy. You just need something that gives you a, a high level, idea of what's going on.
Okay. I think we have time for more questions, and again, there's more questions coming in. Be sure to get your questions in via chat, and we'll do our best to follow up with those in an email. But let's wrap things up with what other analytics tools can be used in Hadoop?
So there's several different ones that can be used. Primarily, if you look at just basic Hadoop technology, Pig, the Hadoop scripting language, can be used as almost like an ability to write your own syntax. So, I mean, again, you can program and write your own, basic codes for what you're looking to do. There's also Hive, the data warehouse, which can be used as a basic querying system. That you can use as, again, I like to call it like a local analytics tool that can be used. And then you can, again, there's more in-depth tools out there like, R, which is an open source programming language that's very, it's gotten a lot of adaptation, in the open source community and has a pretty strong following at this point. So it's, really, I would say, good, open source programming language that can be used and applied pretty, simply into a Hadoop environment.
And there's always the option of implementing your own because the map and reduce tasks within Hadoop are ultimately just a piece of code, usually Java, but you can even plug in another language. So while this is not exactly a data analytics tool, but you could always write your own custom implementation, and if you have a sufficiently exotic task, you might have to, in fact.
Okay, we have lots of more good questions, but we're coming up on time, so we'll just wrap it up here, and we will follow up with all the questions that we get. Some of them require a little more in-depth reply, so with that, I'd like to thank everyone for joining and participating with your questions. Again, feel free to send any other questions our way. We'll follow up with them post the webinar. And for more information about data mining and Mahout and Metascale's offerings, feel free to visit our website, metascale.com, or contact us via contact@metascale.com. And with that, thank you, Amit, and thank you, Alex, and thanks everyone for joining.
Thanks for joining, guys.
Thank you, guys.